Just have a look at both of these LEDs. Both are getting brighter and dimmer, and you may think that both of them are using the same logic for fading, but actually one of them is using PWM logic and other is using DAC logic. DAC means digital to analog converter. So in this video I am going to tell the difference between both of them, and I will also give you the reason for the title of this video. So let's get started. Now before stepping further, I want to explain you something. So microcontrollers only understand zeros and ones, which constitutes binary language. But if we talk about the real world is mostly analog and not pure digital, right? Like pressure, temperature, sound waves, or speed of an actuator, and many more. So how do these microcontrollers actually communicate with this analog world? So it has two options. Either it can fake the analog signal coming from the real world, or it can use the specialized hardware. Now let us talk about the PWM. So PWM stands for pulse width modulation, and it is basically a digital signal. But this digital signal is switched between high and low states so fast that we can't tell the difference between an analog signal or a digital signal. So because of this fast switching, this digital signal behaves like a fake analog signal or pseudo analog signal. So in this image you can see this is the low state and this is the high state. Okay, and we are not changing the voltage level. Voltage have only two levels, 0 and 5 volt. 5 volt in case of Arduino and 3.3 volt in case of ESP. What we are actually changing is the duty cycle of the PWM signal. So 50% duty cycle means the signal will be in on state for 50% time and off state in 50% of time. So from here to here this is a complete time period. And similarly for 75% duty cycle, the signal will be on for 75% time and off for 25% of the time. And this fast switching depends on for how much time we want the signal to be in on state and for how much time we want the signal to be in off state. So as we increase the duty cycle, the switching also increases, right? You can see for 75% duty cycle the signal is in on state for most of the time. So here switching is done so fast, and here for 25% duty cycle the switching is being done so slow. Now moving on to the DAC. DAC stands for digital to analog converter, and unlike PWM which uses fast switching between high and low state, DAC uses a dedicated hardware to generate the analog signal. And this DAC is a complex combination of the resistors, and it is also called the ladder logic of resistors, right? And this DAC simply takes digital number in input and produces a corresponding voltage. Now if you remember, I said in the starting that microcontroller has two ways to communicate with the analog world. Either it can fake the analog signal or using the specialized hardware. So this faking the analog signal is this PWM method, and using specialized hardware is the DAC method, right? So in a nutshell, this PWM signal generates the fake analog signal and DAC generates the true analog signal. So if you are enjoying this video till now, make sure you subscribe to my channel for more such explanations. Now the question arises, can we turn the noisy PWM signal, noisy because of fast switching, into DAC-like signal? And the answer yes, we can do so with the help of low pass filter. So if you want a separate video on low pass filter, then comment down below LPF and I will bring a separate video for you. So in this demonstration, this blue LED is displaying the logic for DAC and this green LED is displaying the logic for PWM. Now let us understand this program, which consists of both PWM as well as DAC. So PWM LED is connected to GPIO number 18 and DAC LED is connected to GPIO number 25. Because on the ESP there are only two pins, 25 and 26, which are used for DAC. And here is the PWM parameters. Frequency is 5000 Hz. So the time period will be 1 divided by 5000, which is 200 microseconds. So suppose if the duty cycle is 10%, then the high time will be 1 divided by 50,000 seconds. And similarly low time will be 9 divided by 50,000 seconds. And resolution is 8. It means for the brightness there are only 256 levels in total, starting from 0 to 255. And brightness is initially defined to 0, and this fade amount is equal to 5. It means every time the brightness level will increase or decrease by this amount, 5. Now in the setup function we are defining the frequency and the resolution on the PWM LED using this function ledcWrite. Because we are using ESP32, so we will require this function. But for case of Arduino, we can simply use pin mode. And in the loop function, we are using this function ledcWrite for PWM approach. And for the DAC approach, we are using this function dacAttach. And this if condition is to handle the edge cases. Suppose if the brightness level is less than 0 or greater than 255, then we are flipping the sign of fade amount. It means, suppose if the brightness is negative, then by flipping the sign, brightness will keep on increasing. And similarly, if the brightness is greater than 255, brightness will keep on decreasing. And we are increasing the brightness by this fade amount. Now one important point to note here is that Instead of LEDCWrite, we use analogWrite function for generation of PWM signal in case of Arduino. And if you have been with me so far in this video, then easily you can observe that we are using both the function LEDCAttach and LEDCWrite in case of PWM. But in case of DAC approach, we are only using dacWrite and no dacAttach function. So why is this so? So why didn't we use dacAttach function in our program? So before that, you need to understand about the software mapped peripherals and hardwired peripherals. So if we talk about the software mapped peripherals, it is related with the PWM signal. And inside the ESP chip, there is a switchboard called GPIO matrix. And this GPIO matrix allows us to take the PWM signal generator, which generates a PWM signal, and connect it to a digital pin, which is pin number 18 in our case, right? And this LEDAttach function tells the GPIO matrix to take the PWM signal generator and connect it to pin number 18. Now coming on to the hardwired peripherals, in this case the DACs are permanently and physically connected to GPIO number 25 and 26, and that is why there is no concept of switchboard or GPIO matrix here. And the signal doesn't need to be routed to a specific pin like we were doing here in this software mapped peripheral case. The path is already defined to these pins 25 and 26. And this dacWrite function is also smart enough to handle all the processes. So when it is called, ESP does three processes. First one is the digital pin no longer remains a normal digital pin. Second one is it connects the internal DAC voltage ladder circuit to the specified pin. So here the specified pin is pin number 25. And the third one is it sets the voltage level using this digital number, which is the brightness here. So if you enjoyed this video and learned something new, then hit the subscribe button and like this video. And if you have any doubt regarding this project, comment in the comment section, and I will meet you with a new project in another video. And thanks for watching.